All right, everyone. So this particular video, I'm going to teach you the first kind of concept relating to rocket stability, which is how the center of gravity plays a role in that. And then we're going to use that information to develop a system of equations that we can use to then figure out exactly what lengths we want our body tubes to be. So to get us started, there was a video in this assignment that kind of gave you just an introduction to rocket stability overall. But the big takeaway from that video that you should have gotten is that a rocket, in order to be stable or have a stable flight path, needs to have its center of gravity above the center of pressure. So we'll talk about the center of pressure all separate. For this particular video, we just want to focus on the center of gravity. So we want our center of gravity to be higher up on the rocket than where our center of pressure is. So in this case, the center of gravity is the solid yellow circle, and the center of pressure is the yellow circle with the black dot in it. Now, in addition to thinking about the stable flight of the rocket, we also want to think about the flight sequence. So as the rocket takes off, it's going to have the engines propel it. That's our solid rocket fuel. And they're going to propel it into the air. But at some point in time, the engines are going to stop and the rocket is going to begin to flatten out. So that's called apogee. And when it begins to flatten out, that's normally when the parachute is then going to deploy, and then you start the recovery phase of the rocket flight. So when you're thinking about where you want the center of gravity to be, you also want to think about, is there any way that we can maybe help ensure that the recovery system or our parachute is able to deploy more efficiently, more reliably than the not. And if we look at the way that the engines are constructed, so we have 4 engines in a rocket. 3 of them are what we would call D12 zeros. So they're going to ignite, they're going to burn for a certain amount of time, and then they're going to stop burning, and that's it with that engine. But one of them is what we call a D12-5. So that 5 means it's going to burn just like the other D12s, but then once the propellant is used, there's going to be a delay of 5 seconds, and then there's going to be an ejection charge that's activated. And that ejection charge is going to deploy the parachute. Now, if we go back to our flight sequence here, that ejection should be happening as well when the rocket is in apogee. So it's beneficial when that deployment occurs for the rocket to naturally be separating where the upper and lower stages connect. So if those two pieces are already coming apart, when the parachute deploys, it's not deploying into the upper stage or deploying into part of your rocket. It's deploying out into the atmosphere, where it's less likely to get tangled up, and you have a more successful chance that the parachute is actually going to do its job by slowing the descent of your rocket down. So the way that we do that is we try to get our center of gravity to be located at that specific point where the 2 stages of our rocket separate. So right now you have your body tube in two pieces. And we need to figure out where are we going to cut or trim the upper and the lower piece to ensure that not only does our rocket meet the requirements as far as length and stability and stuff like that, but so that also we manipulate it so that our center of gravity is right here where those two pieces meet. And that way, when the rocket goes into the apogee where it flattens out, gravity is naturally going to pull down on these ends here where we have the most mass, and it's going to separate right there where the coupler is, where the two stages are connected. So you can think of the center of gravity as a balance point. So if I erase all this stuff that I have here and we think of, okay, we want the center of gravity right here. What that means is we're kind of making a balance point right there in the at the intersection between the two stages, and we want the balance of the upper stage to be exactly equal to the balance of the lower stage. And what we're really balancing there is something called torque. Torque is the natural rotation of an object around a point. So in this case, we're talking about rotation around the balance point or the center of gravity. And there's two things that go into measuring torque. So basically what we want is we want the torque on the left-hand side of the fulcrum to be the same as the torque on the right-hand side of the fulcrum, so that overall there's no movement. The two things equal out and they're at equilibrium. So torque is a function of force times distance. So the distance from the center of mass on one side times the force acting on that side, directly being equivalent to the distance on the other side of the fulcrum to where the force is acting on the other side. And in this case, the force is gravity or weight pulling down. So we can kind of ignore the acceleration due to gravity part of it, and we can really just narrow it down to the two most important components, and that is the mass and the distance. So we're going to kind of simplify this into the length or the distance from the center of gravity times the mass on one side should equal the distance or the length from the fulcrum on the other side times the overall mass of the engines. So I've put some estimates in here for you. A single large egg on average is around 60 grams. It can be anywhere from like 54 to a little over 60, but a good estimate is 60 grams. The engines, the four engines by themselves, is 182 grams. So if you want to use those numbers, by all means, go ahead and use those numbers. You can make them a little bit more accurate by actually measuring the mass of your entire engine mount before you install it. But you guys don't really have access to scales, so we didn't do that. Also, normally we would have taken the mass of our crew capsules and gotten a really good accurate measurement of what the crew capsule actually weighed with all of the packing material and things like that in there. You can kind of add a little bit to these estimates. So for example, the engines with the motor mount is probably closer to 200 grams. So you can choose to use that number instead. And the average crew capsule, if you're using something like cotton balls, something lightweight, packing peanuts, is usually closer to about 80 grams. If you use something heavier, maybe even up to 100 grams, depending on how uh, how thick your packing material, things like that are. So you can make those estimates a little bit more accurate. But essentially, um, if we call the distance from the center of mass of the crew capsule to the coupler X, and then from the coupler to the center of mass of the engine mount Y, we have an equation then that X times 80 or 60, depending on which estimate you're using, um, needs to be equal to Y times 182 or 200, depending on what estimate you're using there, grams. So that's the first of our equations that will go into our system for deciding these lengths of X and Y. Now, there's one more thing that we need to think about, and that is the constraints on our length of our rocket provided in the rules. So it says rockets must not exceed 650 grams gross weight at liftoff, and the overall length of the rocket must be no less than 650 millimeters or 25.6 inches as measured from the lowest to the highest points of the airframe structure, including fins and launch configuration. So that means that we have to measure from the tip of the nose cone all the way down to the fins, and that has to be no smaller than 25.6 inches. Now, I know we haven't talked about the fins at all, so you might have a little bit of length added to this based off of the fins, but as just a rough estimate, it's good to just go with like the bottom of the rocket. And if we end up with it being even a little longer because of your fin placement, then that just makes you even more, you know, meeting the expectation of not being less than 25.6 inches. So essentially, our second equation is that top measurement that we made in the last video. So for me, that was 8.25 inches. Plus whatever we decide X is going to be, plus whatever we decide Y is going to be, plus that 1.25 inches, that was the distance between the center of mass of the engines and the end of the bottom part of the body too. So if we add up all of those links together, they have to be a number greater than 25.6. So think back to Integrated 1, Systems of Equations, Chapter 5. We are now having to solve a system of equations, and we're looking for what X and Y can meet both sets of conditions. So not only do they have to measure to be at least 25.6 inches, but they also have to meet the condition of X times, the mass that you decided for your crew capsule has to be able to equal Y times the mass of the engine mount. So we're going to use a graphing calculator called Desmos, and I did include the link to Desmos in the links for this assignment. And essentially what we're going to do is we're going to put both of those equations into this graphing calculator, and that's going to give us our options for X and Y. So we're going to start off, I'm going to use the higher measurement. So I'm going to use the 80 80 times x, and that has to equal the 200 times y. So that's going to make sure that my center of gravity is right there in that connection point between the two stages. And as you'll notice, there's now a lovely red line across my graph that shows me what x's and y's meet that particular condition. And we want to focus only on quadrant 1 where we have positive x's and y's, because it doesn't seem reasonable that we'd have like a negative length of one of our body tubes. And then the second equation, I'm just going to go down in one more box here, and I'm going to put in the second equation. And for me, my top measure was 8.25, and then I want to add that to x, add that to y, and then add that lower part, 1.25 inches. And like I said before, you want to make sure that you're putting your measurements into decimal forms instead of fractions. I mean, this calculator knows what to do with fractions, but it's way easier to do adding and subtracting, multiplying, dividing when you have a decimal than a fraction. And that measurement has to be greater than or equal to. It could actually be equal to. So you can go greater than sign and then add the equal to sign, and it will give you greater than or equal to 25.6 inches. So when I hit enter here, whoops, what did I do? I put a comma instead of a period. There we go. Notice that it's now shaded off this whole top part. So what that means is, in order to meet both conditions, having the center of gravity in the right place and having the minimum condition of the length of the rocket being 25.6, I have to be both on the red line here and in this shaded portion of everything that's over the 25.6. So my options that I have here are any of these points all along the rest of this line. So for example, if I just wanted to go with the smallest I could possibly make it and still meet my conditions, I would want to pick this point where those two lines cross, right here where it's highlighted. My top stage would be 11.5 inches long, and my bottom stage would be 4.6 inches long. That's what that means. X is the first value, Y is the second value. Now, I don't have to pick that one. That's just the most minimal measurements I can make. I can, say I want it to be longer. Maybe I want it to be out here. And so if I pick this point right here, which is one where it's nice and even, the top stage would be 15 inches and the bottom stage would be 6 inches. I could even go, out here where these cross out here and this also crosses. That would be 20 inches on the top stage, 8 inches on the bottom stage. So it doesn't matter to me where you're at up here. That is completely up to you. Just realize that the longer your rocket is, the heavier it's going to be. And we need to go back to our constraints here. Notice that it can't be any more than 650 grams. So the longer the rocket gets, the heavier it's going to be. And notice we already have almost 300 grams worth of mass just in our engines and our crew capsule. That's not counting the body tubes. That's not counting the mass of the parachute, and any the coupler, any of those pieces either. So you definitely want to take that into consideration. But once again, anywhere on the red line, in the blue shaded area above where these two lines cross, are all XY coordinates that satisfy both the conditions of the system. So it could be any of those measurements, and you can get them right off the graph. So once you've decided which of these measurements you're going to use along here, then you're going to want to mark that on your body tube, and you're going to want to trim them so that they are right here, where the coupler is going to be. Now, remember yesterday when I marked the center of mass for my egg, the X measurement that you're making is from that mark down away from the nose cone. And so for me, that would be 11 and a half inches from the X that I put where I want my egg to be down to the end, the non-nose cone end of the body tube. And in the same way, my 4.6 is going to be from where I drew the X for the center of the engine mount, and that's going to be going the opposite direction towards, again, the center of the rocket, not towards the engine mount end of the rocket. So in this case, my upper stage is going to be about twice as long as my lower stage, because this year they're only using one egg instead of multiple eggs. So there you have it. That's how you're going to decide the lengths of your body tubes. So you're going to be carefully trimming them to those measurements. And then in the next video, I will teach you how to make the coupler that's going to hold them together in the middle. And then all we'll have left to do is essentially build our parachute and figure out how we want to design our fins to best ensure that the center of pressure is where it needs to be on our rocket as well. So I hope you've been enjoying this project. I know I have, and I'm excited to see what you guys have come up with, and to be able to launch our designs. Just waiting to hear from Governor Inslee when we get to go into phase 2, so that we can have gatherings of at least 10 people. Otherwise, I don't know, we might just wing it anyway. We'll see how it goes. So can't wait to see you guys in person again. I really miss you all. So have a great day, and I look forward to seeing your rockets.